Hello everyone, and welcome back to what could possibly be our last lecture in computational finance this semester. And we still have to talk about spline interpolation. If you remember what I told you last time, let me just check that. I think I made some... Yes, I showed you this plot here that actually we want to improve on polynomial interpolation in the sense that we still want to get an interpolating function, but we want the interpolating function not to fluctuate and not to oscillate between those nodes as highlighted here with the blue points. So we want the function to be as smooth as possible, and the way to do this is to use a polynomial spline. A polynomial spline is a function that consists of polynomial pieces. I've shown you this here, for example. You have one part like this, and a second one like this, and a third one, and we want to glue those polynomial pieces together. And after having glued all these functions together, we need to make sure that at those gluing points, so to speak, the function that results is sufficiently smooth. So this is going to be a spline. We call this a spline. Nebenbei, auch auf Deutsch sagt man ein Spline, polynomiale Spline-Interpolation. Sie können ja mal bei Wikipedia nachschlagen, wo eigentlich der Name herkommt. Es hängt auch damit zusammen aus dem Bauhandwesen und aus der Bauingenieurwissenschaft. Da nimmt man nämlich dann auch so Splines, hat man früher aus Holz genommen und um Säulen gelegt, die sich dann leicht verbiegen konnten, und daher kommt auch dieses Bild, Splines. So, as we've seen, major disadvantage of polynomial interpolation is oscillation between those nodes. Problem here, for example, if you take this function, the actual function is almost constant until here, then it's a polynomial, goes up, goes down again, and it becomes constant again. So the idea to use different functions and to glue these different functions together is actually makes sense, because it seems as if the function is different in certain parts of the set of numbers we are looking at. Okay. Now, in order to solve this problem and to prevent the function from oscillating, we take polynomial pieces, we glue them together. So in different parts of the definition area, different polynomials are used. And this is viable under the condition that the individual polynomial pieces should be continuously differentiable as often as possible at the seams, at the gluing points. And what results is a polynomial spline, polynomiale Spline-Funktion, oder einfach nur ein polynomialer Spline. So we'll start again with n+1 nodes and supporting points, xi, yi. We have n+1 of these, and we can now use, for the approximation of the function f, on each interval between two nodes, xi and xi+1, a polynomial piece si of x of degree 1. So what we first take is we have x0 here, we have x1 here, and we have x2, let's say here, and we might have x3 here. Don't need to be equidistant. And we can then say, okay, we use this linear function here. We could use a different linear function here, and we can again use a polynomial here. As you can clearly see, this is not an interpolating function that is of any help to us. It is not continuous at the nodes. It is continuous and differentiable in between, but we need to make this function smoother at the nodes. Ja, Sie sehen, diese einzelnen Teilstücke, das wäre ja hier jetzt, Entschuldigung, das wäre S0. Das wäre jetzt, wenn ich das richtig sehe, ja, das wäre S0, das wäre S1. und das wäre S3. Das wären also die 3 Teile, die ich da zusammenschnipsel. Und Sie sehen, an der Stelle hier ist die Funktion nicht stetig, auch damit nicht differenzierbar, hier genauso. Und wir wollen jetzt natürlich den Spline so hinbekommen, dass er an den Nahtstellen, an den Knoten, dass er hier hinreichend oft stetig differenzierbar ist. So, as a first condition, we require the functions to be continuous, so that at least si of xi plus 1 is equal to si plus 1 at xi plus 1. So if the function is equal, coming from the left and coming from the right, because we are looking at polynomials, yes, then here the function will be smooth. It will be continuous. Now, with the Lagrange base polynomials, we have the following. Si this is supposed to be a polynomial, so obviously we can write each S0, S1, S2. Actually, I made a mistake here. S1, S2, this should be S2. Can be written using the Lagrange base polynomials. And then this form of interpolation, if we use the Lagrange base polynomials, is called a linear spline. And the interpolator is continuous, though its derivative is not. It's not continuously differentiable. So what could result is if we take a linear function, if we only take linear functions, and a polynomial of degree 1 is a linear function, it will look like this. Maybe like this. As you can see, this is a continuous function. It's not continuously differentiable, obviously, but this is a first starting point. This is a linear spline. And now to achieve differentiability of the spline, we have to increase the degree of these single polynomial pieces S0, S1, S2 and so on. Sie sehen hier sehr schön, bei einem linearen Spline machen Sie nichts anderes, als einfach lineare Funktionen so miteinander zu verknüpfen, dass sie hier einfach an den Nahtstellen stetig sind. Das ist natürlich nicht differenzierbar, aber ein linearer Spline ist eine erste sehr einfache Möglichkeit, um eine Funktion zu approximieren, wenn Sie nur einzelne Werte kennen. Ich sage das jetzt einfach mal auf Deutsch, weil ich glaube, das ist jetzt auf jeden Fall für die Klausur nicht so wichtig und für das Verständnis vielleicht schon eher. Splines spielen natürlicherweise in der Computergrafik eine ganz große Bedeutung. Denn wenn Sie sich jetzt einfach nur den Bildschirm mal hier anschauen würden, dann sehen Sie ja zum Beispiel hier auch, Sie sehen Buchstaben, Sie sehen Grafiken. Und wenn Sie jetzt mal sich gefragt haben, auch gerade bei Computerspielen, wie schafft der Rechner das denn eigentlich so schnell hier immer das neueste Bild zu erzeugen, wenn ich jetzt also einfach hier die Folie wechseln würde, er muss ja sofort auch letztlich alle Punkte auf dem Bildschirm hier irgendwie füllen. Das, was häufig gemacht wird bei der Computergrafik ist, dass man, ich könnte jetzt mal ein einfaches Beispiel machen, es reicht ja, wenn ich sagen würde, ich möchte ein S zeichnen, den Buchstaben S. Was ich machen kann ist, ich kann nur einfach sagen, ich nehme diesen Punkt, ich nehme diesen Punkt, ich nehme diesen Punkt und vielleicht noch diesen Punkt und sage dann, lege, wenn ich sie so durchnummerieren würde, speichere jetzt nicht hunderttausende Punkte entlang dieses S's ab, sondern speichere 1, 2, 3, 4, 5 Punkte ab und jedes Mal, immer dann, wenn ein S angezeigt werden soll, nimm diese 5 Punkte, berechne den Spline, der da durchgeht und siehe da, ich hätte jetzt etwas besser wählen müssen, siehe da, man bekommt ein S. Und offensichtlich ist jetzt hier natürlich das, was resultiert, ist ein ganz simples Polynom, ein polynomialer Spline. Und Polynome können relativ schnell ausgewertet werden. Das heißt, ich muss dann einfach nur noch hier, das ist ja eine Funktion, zweidimensional jetzt in dem Fall. Ich muss in diese Funktion dann einfach nur noch vielleicht 100 Werte einsetzen, 100 Polynomwerte ausrechnen, das schafft Ihr Taschenrechner schon relativ schnell, ein guter Computer natürlich in 0, nichts. Und so funktioniert an vielen Stellen Computergrafik. Sie werden nicht alle Punkte, alle Pixel von hier oben links bis unten rechts, werden Sie nicht immer abspeichern und schon gar nicht in Computerspielen, wo das Ganze ja dynamisch in Echtzeit passieren muss, sondern das, was häufig gemacht wird, ist, Sie nehmen im Grunde genommen sehr viele Punkte. Die Punkte bewegen sich Und alles, was dazwischen abläuft, wird letztlich immer in rasender Geschwindigkeit so einfach wie möglich, aber so gut wie möglich approximiert. Und dann werden die Punkte einfach der approximierenden Funktion, also in dem Fall hier der interpolierenden Funktion, die werden ausgewertet und das wird angezeigt. Wenn Sie sonst hier immer alle Pixel anzeigen müssten und alles abspeichern müssten, würde Computergrafik nicht funktionieren. Gut. But that only on a side note. So next we use 3 polynomials, actually more polynomials, but with grade 3, of degree 3. We have now 4 coefficients, si0, si1, si2, si3. So as you can see, we have polynomials of degree 3, that is x taken to the 3rd power, x taken to the 2nd power squared, and x, and a coefficient, actually an intercept. And we now require, first of all, that this condition here is fulfilled. S of xi is yi. This is the interpolating requirement. That is, that if we insert xi, yi, that actually the interpolating function, the spline, yields the function values yi as function values for xi. The second requirement is that si at xi plus 1 is equal to si plus 1 of xi plus 1. That's again the requirement that the resulting interpolating function is continuous. But we also require that the derivative, the first and the second derivatives of si equals the first and second derivative of si plus 1 at the nodes. In other words, they have the same first derivative and the same second derivative, meaning that it's continuously differentiable. So the function s, which results as the spline from which which results by gluing together these functions s1, s2, s3, is called a cubic spline, ein kubischer Spline. It's twice continuously differentiable. The spline has 4 times n coefficients, but due to the continuity requirements, 3 times n minus 1, and the interpolating property, that was the first one, n plus 1, we've only used 4 times n minus 2 degrees of freedom, and consequently we can set 2 conditions additionally, and some common requirements are, first of all, that we require the second derivative of s at x0 to equal the second derivative at xn being equal to 0. So actually it will start like this. We'll go back like this. It's called a natural spline, or we can require additional things. Now, to see what happens in MATLAB, we have to solve a system of linear equations. We've seen this before. And this is already done in MATLAB. Actually, this is a function interpol, and we can set the condition, the option to spline, in contrast to polynomial. And then we have x equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and those function values y. And as you can see, this is the resulting spline. It's not a polynomial. The polynomial will probably look like this. Go through here, oscillate again, go through here, and so on, and like this. And the spline looks sufficiently smooth. So a spline interpolating function is much, much better suited for function approximation than a polynomial. Okay, you can also use the function spline, same thing here, x, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then we use spline of x and y and plot the result. Now, to illustrate the advantage of spline interpolation compared to polynomial interpolation, again we'll consider the example of the Runge function. We do spline interpolation. We use the polynomial interpolation with equispaced points, etc. And then we use actually 11, 20, and 21 equidistant and equispaced points. And let me delete those. First thing you need to see is that if you remember, let me just see, where was the polynomial approximation? I think for the, yeah, it looked, actually delete all this to make it clearer. This was even the better version using the Chebyshev supporting points. As you can see here, with the with the usual equidistant supporting points, it oscillated up to 6 on the x-axis, y-axis. Sorry. For the Chebyshev supporting points, it oscillated well between 0 and 1, even before reaching its peak. And now, if you have a look at the Spline Interpolation, you can see that it's with 11 points, it starts to oscillate just a little bit around here. But if you use 20 or 21 equispaced points, you can see that, well, the approximation is actually very, very good. Yeah? You have a little bit of approximation error here and here, but this is okay compared to the highly oscillating polynomial before, right? Okay, so we can see that an increased number of nodes obviously leads to an improvement in approximation quality. However, one has to be careful. Actually, one additional point can do a lot of, can make a huge difference. As you can see here, actually the approximation here is not too well, and it's due to the fact that we used an even number of supporting points. And additionally to the cubic splines, there are of course numerous other types which we are not going to present here in this lecture, but cubic splines are a good starting point for any function approximation. And why are we looking at splines in the first place? Well, because they're used for approximating the term structure of interest rates. And that's what we'll discuss next: term structure of interest rates and interest rate models. Now, why do we need this? We need risk-free spot and forward interest rates in any context in finance, actually. We always use in our models, but also in practice, we always are led to the risk-free rate. And when we talk about the risk-free rate, it's usually a risk-free spot rate. And in practice, in reality, we usually have more than one spot rate and more than one forward rate. First of all, to remember, what is a spot rate? A spot rate is the interest rate you have to pay now for lending and borrowing capital now. The forward interest rate is the price, the interest rate you agree upon right now for lending and borrowing in the future. For example, you can now enter a forward contract if you know that, for example, in 2 years you need a loan. Well, then you are led to the forward rate, the forward interest rate. These are risk-free interest rates here we are looking at, so usually they will result from government bonds. These risk-free interest rates inevitably result from a term structure of interest rates, or just the interest structure, the term structure or the yield curve. What is the term structure of interest rates? Every time you hear something starting with the term structure of yada yada yada, it means that it's a function where on the x-axis you have an investment horizon or maturity in, let's say, years, and on the y-axis you have, for example, in this case, the spot rate. Now let's call it the interest rates I. Then if yes, yeah, let's write it out. So this is not the yield, but this is in years. So the term structure of interest rate will probably look something like this. It will start with a low interest rate for a low maturity, and with a higher, longer maturity, it will increase in interest rate. This is called a normal interest rate structure, normale Zinsstrukturkurve. If, however, it looks like this, like this, then this is an inverse yield curve. term structure of interest rate, and this one is a flat one. In German we say normale Zinsstrukturkurve, flache Zinsstrukturkurve oder inverse Zinsstrukturkurve. Now, how do you estimate these? How do you estimate these term structures of interest rates? Well, actually using spline interpolation, and this is what we're doing in this section. Now, we start with a zero bond as a very simple type of a bond, which is sometimes emitted by governments. Then you have sovereign bonds, government bonds. The zero bond with a maturity t and a nominal value of 1 monetary unit has, if we can neglect default risk, which is the usual setting, at least for most countries, at the time t being smaller than capital T, has a price of P, depending on small t and capital T, small t being smaller than capital T. And at maturity, the price is 1, because you know that at maturity, you're getting repaid 1 monetary unit, so the price has to be 1. And this function that relates the maturity t to prices of a zero bond is called the discount curve, or the maturity structure, the term structure of zero bond prices. Why? Well, think about this in the following way. Okay. Now, we have 1 monetary unit that is being paid. It's a zero bond, so we have no coupon payments, and at the end we get +1. So what is the price of this zero bond? Well, it's 0 divided by a discount factor. It's +0, again divided by a discount factor, plus, and so on, +1 divided by a discount factor. If we have 1 divided by the discount factor, actually the price is the discount factor. If we don't have any coupons, you can actually see that the price, let me write this down, the price from t to capital T is actually 1 divided by 1 over 1 plus r taken over the remaining maturity of this payment, of this bond. So in other words, this is just the discount factor. And this is why it's called the discount curve, and the maturity structure of the zero bond prices. Ganz typisch in der Finanzmathematik ist es so, dass Sie Bonds und gerade Zero Bonds immer auf den Nominalbetrag 1 normieren und standardisieren. Wozu führt das? Ganz einfach, dass dann nämlich letztlich die Preise, die Sie hier haben, dass die Zero-Bond-Preise am Ende nichts anderes sind als die Diskontierungsfaktoren. Denn, wenn Sie sich das mal anschauen, es gibt keine Couponzahlung zwischendurch. Am Ende kriegen Sie eine Geldeinheit. Um auf den Preis zu kommen, ist ja klar, dass dann letztlich der Preis sich einfach ergibt aus der einzigen Zahlung, nämlich 1, abdiskontiert über die Restlaufzeit groß t minus klein t. Und damit ist der Zero-Bond-Preis hier letztlich der Diskontierungsfaktor, also dann invertiert. Und damit haben wir die erste Kurve, die erste Fristigkeitskurve, nämlich die sogenannte Discount Curve, und die gibt Ihnen an, für unterschiedliche Restlaufzeiten, für unterschiedliche Maturities, Fristigkeiten, diese Diskontierungsfaktoren, die dann natürlich dann auch immer weiter abfallen. Okay, so this is the first term structure we can consider. The next, we can look at the continuous forward rate. The continuous forward rate is given by dividing the prices for the zero bonds between 2 points t and s, and this has to be equal to the continuous interest rate We can also do the same with the instantaneous forward rate. This is simply taking the limit of the continuous forward rate with the time difference between t and s being very small. And if we now take this instantaneous forward rate, so the forward rate that starts at one point in time t for lending and borrowing for an infinitesimally smaller amount of time, we get the so-called forward rate, the forward curve. And then we can calculate the spot rate with constant interest rate based on the zero bond prices with continuous discounting. We have that the price P T capital T has to be equal to this expression, and thus we get the zero bond returns, the yields of the zero bonds. And if we write this down as a function, maturity related to the interest rates, to the constant interest, this gives us the yield curve or the maturity structure or the term structure of interest rates. Das ist die, auch im Deutschen sagt man häufig Yieldkurve, das ist die Fristigkeitsstruktur der Zinssätze, das ist die Zinsstrukturkurve. Warum? Weil sie letztlich hier die Restlaufzeit, Groß T, die Fristigkeit abbilden auf den Spot-Zinssatz. Also wir haben dann drei Kurven. Spot-Zinssätze, Forward-Zinssätze und die Diskontierungsfaktoren oder Zero-Bond-Preise. Alle drei sind, wenn es denn arbitragefrei ist natürlich, das muss man dazu sagen, wenn der Markt arbitragefrei ist, sind alle drei Kurven äquivalent. Sie können aus der einen die anderen beiden berechnen und umgekehrt. Also Sie können von einer zur nächsten springen. Now, in all theoretical interest rate structure models, a yield or forward curve is often assumed as a function of the continuous maturity t. This is obviously not the case in reality, since we only have discrete quotes of interest rates which are given throughout, let's say, maximum maturity of 30 years. Therefore, we need to approximate the maturity, the term structure of interest rates. And in the following, we'll give some few examples how this can be done, for example, using splines. Now, what we need to do is we need to approximate the current, for example, the discount curve. That is, x is defined as a function to d of x, and this function d, the discount curve, is given by the zero bond price for a maturity from t0 to t0 plus x. So for example, if x is 5 years, this would be the zero bond price of a zero bond that runs for 5 years. Now, this can be achieved by the approximate solution, p equals c times d plus epsilon. What is this? P is the column vector, der Spaltenvektor, of the market prices of a finite number of interest securities. We have a finite number of zero bonds in the market, and we have the prices for these. If we have a fixed income product, a zero bond or a coupon bond, we do know the nominal payments, the nominal cash flows of this bond, and thus we have the matrix of cash flows C. Now, to get to the prices, we need to write P on the left-hand side, and on the right-hand side we have to take the cash flows of those bonds, and these need to be discounted. However, the discount factors need to be the same if the market is arbitrage-free. The discount factors need to be the same for all securities in the market. So C is the matrix of cash flows, D is the vector of discount factors, and epsilon is actually a residual vector of pricing errors. Ideally, we would have no pricing errors, thus epsilon would be the zero vector. And the cash flows, these will result in the events T0, T1, and so on, and we'll consider a bond market, an actual example with real data. So we are looking at the prices of British bonds, so-called UK gilts, on September 4th, 1996. We actually do have the day account convention. We don't need this. And there is a semi-annual coupon payment. So we first need to estimate the price vector. I actually write down the price vector. This one is given. For example, the first price is I think it should be a point here. It's 103.82, 106.04, and so on. We do have the points in time for all bond payments, and actually this is where this gets nasty. Why? Because these dates, they do not match from bond to bond. So you have to consider all dates. And it will be, C will be a matrix with a lot of zeros. It will be sparsely, very sparse matrix. And we have the payments and the bonds. So this is the cash flow matrix C for our calculation. This is the table with the data. We have the coupon payments. We have 9 bonds. When the next coupon is due, we have the maturity dates and the so-called dirty prices. What are dirty prices? Now, actually, if you buy this bond, not exactly on the payment day of the next coupon, then you would buy into a bond for which someone else has kept the bond, has owned the bond, but who will not see the next coupon payment, and will not receive the next coupon payment. So you have to compensate the previous owner of the bond for the number of days he or she has kept and owned the bond and will not receive a coupon payment, a partial coupon payment. So if you now correct those dirty prices for at least partial coupon payment, then you get the clean prices. Ja, das ist also auch, nennt man im Deutschen die sogenannten Stückkosten. Wenn Sie nämlich einen Bond halten und den zum Beispiel erst einen Tag vor der nächsten Couponzahlung kaufen würden, dann würden Sie ja die gesamte Couponzahlung bekommen, obwohl Sie den Bond eigentlich nur einen von 365 Tagen gehalten haben. Deswegen müssen Sie dann den vorherigen Besitzer entschädigen, und deswegen unterscheidet man hier die Dirty und die Clean Prices, und die Differenz, die Entschädigungszahlung, sind die sogenannten Stückzinsen. Now the matrix C, as I said, is sparse and it doesn't look nice. We have 2, 4, 6, 8, 9 lines for 9 bonds and a huge number of columns because all those coupon dates do not match perfectly. So there will be a lot of zeros here. Now, this is the matrix C, and we now will now try to estimate the discount factors using cubic splines. So we take cubic splines with q plus 1 nodes, psi 0 up until psi q in the form sigma. That's the spline, that's the function. And as you can see here, this is one way of writing down a cubic spline using this function here, which means that actually if this is, where's my cursor here? If this is positive, you take this difference. If it's negative, it's 0. The spline has q plus 3 parameters, and we now introduce 6 additional knots, which is psi minus 3, psi minus 2, psi minus 1, psi 0, up until psi q, and then on the right side, 3 additional knots. We obtain a base of the cubic splines. I forgot to mention this. Cubic splines, again, are a vector space. Thus, all splines can be represented using a base. And in this case, a base is given by the so-called B-splines. Die kubischen Splines sowie die Polynome bilden einen Vektorraum. Ein Vektorraum hat beliebig viele Basen. Und eine Basis des Vektorraums der kubischen Splines ist gegeben durch die sogenannten B-Splines, die Basis-Splines. So we have q plus 3 B-Splines. These are given by this equation here. We need to memorize this. And we will now use the B-Splines as a basis to write down the cubic spline, which is used to approximate the function d, which is the function that gives us any discount factor for all these nodes, for all these dates, and possibly also in between. So this is what we are calculating. So we still want to determine the discount curve, but we are using cubic splines, and the cubic spline we are trying to estimate is represented by using the B-splines, which form a basis of the linear space of cubic splines. Now, consequently, one has the following. D is the function, it's given by all those different discount factors, and it's actually the set of B-splines. These are the B-splines. And we have a linear system of equations, and we have some parameters, z1 until zm. This brings us to a linear optimization problem. What do we need to optimize? Well, we take the price vector, P, we subtract the cash flows times D. This is actually D. Remember? That's my cursor here, okay. This is actually D, the discount factors. But we are substituting D by phi times Z. Z are the parameters of our B-splines. And this together, C times phi times Z, that's, let's call it P dash. These are the theoretical prices. These are the actual prices. These are the theoretical ones, which should result, if we are given the discount factors, we take the difference, we square it, and we minimize this expression with respect to Z. So we are looking for the parameters, the coefficients in this function, the coefficients in the linear combination of B-splines that gives us the cubic spline that minimizes the difference between P and the theoretical prices. The squared error, actually. Ich sage das kurz nochmal auf Deutsch, damit das hoffentlich jeder verstanden hat. Was wir machen ist, wir suchen die Diskontierungsfaktoren, die den Pricing Error, den Bewertungsfehler hier minimieren. Was haben wir als Bewertungsfehler? Die quadrierten, letztlich absoluten Differenzen zwischen, das ist eine Vektormetrik hier, eine Vektornorm. Wir nehmen also den Vektor P, den Preisvektor, die tatsächlichen realen Preise, hier P. C mal Phi mal Z oder C mal D sind die theoretischen Preise. Das sind die Cashflows, diskontiert mit irgendeinem beliebigen Satz an Diskontierungsfaktoren. Wenn wir dann hier die Norm wählen und das Ganze quadrieren, dann ist das der Bewertungsfehler mit dieser Norm so bestimmt. Wenn wir jetzt dann Z, die Koeffizienten für die B-Splines, also die Basis-Splines in dem kubischen Spline so wählen, dass das hier minimal wird, dann haben wir ja offensichtlich einen Spline gefunden, der die Funktion D, die Diskontierungsfaktoren, so gut approximiert, dass wir im Grunde genommen die tatsächlichen Preise vollständig erklären können. Das ist die Optimierungsaufgabe. Now, if the matrix A equal to C times phi has full rank M, we do have a unique solution, and this one is given by Z star equals to A transpose times A, all is inverted, times A transposed and multiplied by P. So this is the usual least squares solution, and we can do this here. We can also require that actually here in this case, if we insert 0 and Z, that this should be given by 1. And as a basis, we will use 8 B-splines with 12 nodes. And you can actually do this at home. You can use the Excel file Zinsstruktur. It's already prepared for MATLAB. And you have the MATLAB Zinsstruktur text file. This is actually the old name. This should be in Moodle. And if you take this, you can enter it right into MATLAB or Octave. And then you can do the same function approximation that is shown here. First of all, we need the B-spline. This is simply the definition of the B-spline coded in MATLAB. Continues here. Next, we have our vector of nodes. We have the matrix psi for the B-spline approximation. We have 104 values and those 8 B-splines. And then the target function in this case is function handler is the sum of P transpose minus C times psi times Z and squared, and then we need to optimize this. So we use f min unc, we minimize the function f, and we start at discount factor 0, 0, 0, 0, 0, 0. Now Z star, these are the optimal coefficients of the B-splines in the representation of the cubic spline, that is the set of discount factors. These are not discount factors of here, but these are the optimal coefficients. The function value is actually 0.1, meaning that this is the squared pricing error, which is okay, it's not 0. We need to keep this in mind. So let's calculate the spot rates for all time points in t. Spot rates, zeros, actually we take minus the logarithm of phi times z star divided by t. Phi times z star, so phi times z star is actually what? It's that these are the discount factors. So we take the discount factors and revert them into the spot rates. Same for the forward rates, and then we can plot these three curves. First of all, the discount, then the yield, and then the forward curve. This is the yield curve using B-splines. As you can see, it starts out at 1. If we have a payment that is due now, we don't need to discount this, so actually this is 1. If we have a payment that comes in, let's say 30, 20 years, the discount factor, the discounting effect will be very high. This is the yield curve. As you can see, for this data in the mid-90s, actually spot rates were between 5, 6 and up to 8%. Nowadays it will probably be 0.1% and so on. So the curve will be much lower, probably more like this. And this is the forward rate. Actually, this says yield curve, but actually, remember, this is the discount curve. This is the yield curve. This is correct. So let me just correct this. This is the discount curve. This is correct. And this is the forward curve. Okay. So that's the approximation using a spline function, actually a cubic spline represented as a linear combination of B-splines. Now we can move next to exponential polynomial curve families, exponentielle Polynomkurven. This is actually very close to what is done in central banks. Now we will look at exponential polynomial curves, and this family includes two models, Nelson-Siegel and Swenson, which are still used by most central banks to estimate the yield curve. So let first x be our variable. F of t0 plus x is the forward curve that needs to be approximated, and we say that it's a function phi of x and z, and we again have coefficients z. Now we say that the discount curve is given by this function. The discount curve has this special, this is my cursor, has this special form that we say the discount factor is given by the exponential function of minus the integral from 0 to x over this function phi with a parameter space z. Now, as before, we want to estimate the coefficients of this discount curve. And again, we minimize the pricing error. The actual price is P minus the discounted cash flows, and the discount factors are again given, in this case, by this, in this form. Okay. The same as before. And the first variant of this model is the Nelson-Siegel model. In this case, the yield curves are given by actually this relation, z1, that's the parameter, plus z2 plus z3 times x, times the exponential function of minus z4 times x. Now, Nelson-Siegel, the curves that can result from these four parameters, they are characterized by a hump. So actually it can look like this. Okay. Now, is this realistic? Well, we've seen, we estimated this using a spline. Actually, it can look like this sometimes, but actually it can also look like this. So it might be that Nelson-Siegel is a good start. Might be that we need more flexibility. For this, we can use the Swenson model. Swenson is an extension of Nelson-Siegel with 6 parameters. So it allows actually not for one hump, but 2 humps. It's smooth, It's a parsimonious model. It only has 6 parameters, and the function, the curves actually are given by z1 plus z2 plus z3 times x times the exponential function plus z4 times x times yet again the exponential function. So both Nelson-Siegel and Swenson, both models belong to the family of exponential polynomial functions. These have a very general form. It's a polynomial function, p1, a polynomial, times the exponential function, plus a second polynomial, again, times the exponential function. That's why they are called exponential polynomial functions. And based on the bond data, not in the last lecture, but actually in this lecture, we can now estimate the term structure of interest rates using Nelson, Siegel, and Swenson. Actually, this is done by central banks. First of all, we need to calculate the theoretical prices. We define this function, theor price. We have z, t, and binary or binar. This is a variable. If it's 1, we say it's Nelson-Siegel. For everything else, it's supposed to use the Swenson model. So this gives us phi. We code the Nelson-Siegel exponential polynomial function and the Swenson one. It's a little bit more complicated. And then we say, well, using these functions phi, we can then use the discount factors. It's a vector of zeros at start, and then we calculate each discount factor. Now we start out with phi, but actually this is what? Traps. What is traps? Traps is the MATLAB function for the trapezoid rule or trapezoid method. Das ist die sogenannte Trapezregel für die Quadratur oder Quadratur. Was ist Quadratur? Quadratur bedeutet die numerische Lösung von Integralen. Was ist damit gemeint? Ganz einfach. Erinnern Sie sich mal an Ihre Schule. Riemann-Integral ist was? Wenn das zum Beispiel hier die Funktion ist, die Sie integrieren möchten, zwischen diesem Bereich und diesem Bereich, was ist das ganz simple? Habe ich das irgendwo hier? Ich habe doch hier bestimmt. So, ja. Habe ich hier keine geometrische Form? Das ist aber schade. Ich dachte gerade, ich hätte hier auch Kanten, nein, und Kästchen. So. Erinnern Sie sich mal, was machen Sie in der Schule schon? Sie bilden die Riemann-Flächen. Sie bilden doch hier so Riemannsche Rechtecke und Sie approximieren die Funktion, indem Sie die Rechtecksumme bestimmen. So zum Beispiel. Das ist die Art und Weise, wie Sie das Integral bestimmen. Das Riemann-Integral ergibt sich ja gerade als Grenzwert, wenn Sie jetzt diese Längen der Rechtecke gegen 0 gehen lassen. Und dann haben Sie natürlich im Grunde genommen nur noch feinste Striche, die hier runterragen, und dann können Sie das Integral dann hier so definieren. Die Trapezregel, man nennt das eben numerisches Integrieren, nennt man Quadratur. Wenn Sie jetzt hier die Trapezregel ansetzen, dann ist das einfach eine Möglichkeit, wie man hier zum Beispiel so ein Integral numerisch approximiert, und das ist wunderbar hier in MATLAB schon implementiert, mich mit Traps, ja, für die Trapezregel, Trapezoid Rule. Okay, so as you can see here, this is the integral, this is the exponential function of what has previously been calculated as the approximated integral, and this gives us the discount factor. And the result is cash flows times discount factors, and this is why we call this theoretical price. It's just the discounted cash flows. Now, the target function, the objective function, is the sum of the difference between the theoretical and actual prices. We use F-min-Anc. Again, we get 4 parameters now, z star, 00898, minus 0.001, 0.0, and so on. These are the 4 parameters. The pricing, the square pricing error, and this is what we get. We have one hump at the start, and this is the yield curve estimation according to Nelson-Siegel. If we now actually were to use the second, if we didn't use binar equal to 1, but if we set it, for example, to 0, we would get the Swenson model, in which case we would have 6 optimal parameters, optimized parameters, and then we could get an additional hump in our yield curve. Okay, so this is yield curve, term structure of interest rate modeling, how it's done in practice. And last but not least, let's have a short look at some interest rate models. Now, we always need interest rates. As you've seen before, for the valuation of fixed income products, we need interest rates. We need discount factors so that we can take those discount factors, discount cash flows in the future, and calculate our prices and make our valuation. Now, interest rates are also, in reality, stochastic. So interest rates change. They might change stochastically, and we need models for stochastic interest rates. Now, in the insurance sector, stochastic interest rate models are particularly relevant for valuing and for the market consistent valuation of technical provisions. Why? Because if you have even a slight background in actuarial mathematics, you might know that it is very important when you are building your technical provisions, also die versicherungstechnischen Rückstellungen, when forming the technical provisions in actuarial mathematics, you need to be sure about the interest rate you're using, because it makes a huge difference. If you think about especially life insurance, we are talking about contracts that will run maybe 30, 40, 50 years. If you have the slightest error in the assumption on your interest rate model, then this error will amplify a lot over the lifetime of your life insurance contract. So also in internal models under Solvency II, we need to think about stochastic interest rate models, and this is what we'll be doing on the very last 20 slides of this lecture. Now, short rate models offer an approach to stochastic interest rate modeling that is frequently used in practice because of their simplicity, both for valuation but also for risk management. And they describe the dynamics of the short rate given by a diffusion process as a solution of a stochastic differential equation. We've already seen this, the Ito process. So actually what we are doing is we are taking the same stance as in the Black-Scholes-Merton model, and we are assuming a diffusion process, an Ito process, for the short rate, short interest rate, RT. So we are assuming there's a drift component, B times dt, plus a diffusion component, sigma times the change in the Wiener process. And we'll now focus on valuation. We'll have a filtered probability space, usual assumption here. P is the probability measure we are looking for, and the short rate is what we call an adapted process, ein adaptierter stochastischer Prozess. Meaning what? At each point in time t, this process reflects the available information up until point t. If there is new information on the next day, the price will react to this and it will reflect all available information. Now, in the valuation model, the money market fund, KT, equal to exponential function, integral of RS, we've already seen, this is a way of writing down a discount factor, is selected as the so-called numéraire. Actually, this is not how it's written in French, unfortunately. It's a numéraire. And this is what is meant by numéraire. This is something frequently done in financial mathematics, and this is very convenient. You take a risk-free money market fund, in this case KT, and you take the price of this money market fund, risk-free, and you express all prices of risky assets as multiples of the numeraire. In this way, you standardize all prices using the risk-free rate. This is done almost always in financial mathematics. Ich sage das auch nochmal kurz auf Deutsch. Man nennt das auch im Deutschen das Numeraire. Was ist damit gemeint? Letztlich, wenn wir jetzt mal sagen, Sie machen das eigentlich an so vielen Stellen. Sie können ja sagen, in welcher Einheit drücken Sie denn jetzt den Preis eines Schuhs aus? Ja, in Einheiten von €1. Was wäre denn, wenn Sie jetzt sagen würden, Sie geben jetzt diesen Preis an in Einheiten eines Apfels? Ja, dann müssten Sie es umrechnen. Und nichts anderes tun Sie jetzt hier eigentlich. Sie nehmen die risikolose Anlage. Das ist jetzt hier in dem Fall einfach ein risikoloser Money Market Fund, KT. Sie sehen ja schon, das ist der Diskontierungsfaktor, ist also wieder auf 1 standardisiert. Wunderbar. Und dann drücken Sie alle Preise später aus als Vielfaches des Numerairs. Das heißt also, dass letztlich alle Preise auch schon die risikolose Anlage direkt widerspiegeln. Wenn Sie nämlich jetzt eine riskante Anlage haben und ihr habt einen Preis von 2, bedeutet das, die liefert also das Zweifache des Preises der risikolosen Anlage. Macht das Rechnen hinterher einfacher, weil Sie haben im Grunde genommen überall schon das Diskontieren mit der risikolosen Anlage hinter sich, wenn Sie nämlich einfach dann das hier als Numeraire verwenden. Now, if the money market fund is used as the numeraire and the only product, then models are generally incomplete. We'll see about this. Now, arbitrage pricing theory now implies that a consistent valuation in models for the short rate are given by the following. We have as central products only zero coupon bonds. Prices are again given by P, T, capital T, the price of a zero coupon bond which is at maturity is 1. And in the absence of arbitrage, if this is an arbitrage-free market, we know that there exists an equivalent martingale measure, Q, and this is, if you don't remember this is a result of the first fundamental theorem of asset pricing. There exists an equivalent martingale measure Q, so that the discounted prices, we take the discounted prices, P, divided by the money market fund, which is supposed to be risk-free, the numeraire, that these form a Q martingale. So what you're doing is, you take the prices of the zero bonds, or the risky assets, you divide them, you express them as multiples of the numeraire, which has to be risk-free, and if they form a Q martingale, then the market is arbitrage-free. Also Sie nehmen letztlich alle Preise von Wertpapieren, drücken sie aus als Vielfaches des Numeraires, risikolosen Numeraire, und wenn dann die resultierenden Preise ein Q-Martingale bilden, dann ist der Markt arbitragefrei. And risk-neutral evaluation by a suitable martingale measure then provides all prices. You simply take the expected value under Q of those discount factors, and thus you have the prices. So these are the arbitrage-free prices for any risky zero coupon bonds. Now, it now continues with the Gerzano theory. As you can see, this gets rather complicated. I would say we can leave this out here. I think it suffices to see that you take the money market fund, you use it as a numeraire. This is done all the time in financial mathematics. You then have to show that the discounted prices form a Q martingale, and then you can actually calculate the consistent arbitrage-free prices for any risky assets. You can then have a look at the remaining slides. We take a look at the Gerzano theorem, the market price of risk, the Valuation model. The Valuation model is one example. Again, it uses a special type of a diffusion process to model the short rates, the short interest rates. But this is only one type. Led to a so-called Feynman-Kutch partial differential equation. This is where it gets rather complicated from a mathematical point of view. We also have affine models, again for the zero coupon bonds. Actually, we have to solve a Riccati differential equation. Again, the Valuation model, and so on and so on. And the Cox-Ingersoll-Ross model. It's interesting to see that this is actually a slightly different diffusion process, and we now have an additional volatility here in the diffusion component, and it's characterized by mean reversion. And we also have a short description of the Hull-White model. You might remember Hull, John C. Hull, the author of the textbooks on options, futures, and derivatives. Only that you've heard these names. And then actually we also have Heath, Jarrow, Morton. Those are the most prominent interest rate models. Heath, Jarrow, Morton, Cox, Ingersoll, Ross, and Valuation. Those are the famous ones. They all use some kind of diffusion process, as can again be seen from this equation. And if you are ever in need of having a look at these models, you've now heard these names, you know that these all are models for interest rates in this context. Okay. Again, I would say, and let me just make this very clear on these slides, that we actually stopped before the Gerzano theorem, which is, I think, way too much. So everything up until slide 550 is relevant for the exam, and beyond that, I think we can do without the slides in this year. And yeah, so I hope you enjoyed this little excursion into computational finance, into the different methods to use numerical analysis in the context of finance, pricing options, using more sophisticated models, especially in MATLAB, in financial applications. And if you have any questions, please stay in the Zoom room. Otherwise, this will be the end of the lecture. You will find all recordings on YouTube in a bit of time, and good luck with the exam. Thank you.